This lecture will cover the introductory to statistical testing, and basically we'll just do the first component to that, which is listing the null and the alternate hypothesis. This is something you'll have to do for every type of statistical test, so it's a good idea to get a really good understanding of this before moving on. So the null hypothesis, to start there, is usually denoted by the notation H with a subscript of a O or a 0, and the alternate is H with a subscript of a 1. Different books might use H sub 0 and H sub A for alternate, but for this book it uses H sub O and H sub 1. There is a definition of the null hypothesis in your book, and the book statement there is, this is the statement that is under investigation or being tested, and it kind of goes on to some other things. I like to say that it's the original claim that you're trying to find evidence against. So mainly, if you can find evidence against this claim, you can accept the alternate, which the book definition here would be the statement that you would adopt in a situation in which the evidence is so strong you reject the null hypothesis, right? So basically, you have an original claim. If you can find evidence against the original claim, you accept the alternate, and now you would have a new norm that would be considered what the population might be accustomed to now instead of in the past. An easy example just kind of relate. I think most of us know that the diastolic blood pressure was like 120/80, so the diastolic would be the bottom number, or that 80. So that might be original claim that blood pressure is 80 for the diastolic number. But if there was certain research done to prove this number either was higher, lower, or just something different, you'd accept some new norm to now say that blood pressure is less than 80. So we'll get more to the specifics, but that's the idea, that you'd have some original idea, present some sort of study and evidence, and then either accept the alternate or kind of keep what was considered the norm. So all of this is dependent on the type of test that is presented to you. So there are three types of statistical tests. Just making sure we can see everything correctly here. Sometimes my tripod gets hit, and I want to make sure you guys can see everything. So there's a left tail test, a right tail test, and a two tail test. Now these are important just to kind of summarize what you're actually testing for, and there are keywords to kind of denote what each test you might be using. So for instance, if you see the word less than, you'd be in a less than case denoted by a less than sign for the alternate hypothesis. If you see greater than or more than, something along those keywords, you'd be dealing with a right tail test, and your alternate hypothesis would involve a greater than sign. And last, you have a two tail test, and the keyword here is differs. If you see the word differs within a problem, you'd be dealing with a two tail test, and here you're essentially finding a probability on both sides of the bell-shaped curve. Now, it's important to note here that your null and alternate hypothesis, you have mu is equal to some value k. This k will be given in the problem. And notice for each of these scenarios, the number in this case, I didn't notice the letter now, but ultimately this will be a number. You see the k expression involved with both the null and the alternate hypothesis. And then basically you're just going to change the sign. Is it less than, greater than, or not equal to? And that's just dependent on the wording of the problem. Okay, so after having those three cases, you would simply just find this thing called the p-value, and we'll talk about what that means here in a second. But the p-value is basically one of the more major components of all statistics, right? P-value stands for probability value. Okay, so we'll start to kind of get moving along here. So going through a few examples. Basically, you're looking for a few keywords, and in the first example here, a teacher feels that playing music during an exam will improve exam grades. So right here, improve. So state the hypothesis that if in the past her average exam grade was 73%. So right now, the original claim is that this teacher claims that her students would score 73 on their exams. However, will playing music improve this grade? So here you're dealing with a right tail test. and you would use a greater than sign in this case, right? So you see mu is equal to 73, that's the original claim. And the alternate hypothesis, mu is greater than 73, because if it's found that music would improve the test grades, you then accept this alternate claim that the test average would be greater than 73. Next, Miles is a beagle that gets regular checkups on his heart. Dogs of this breed are known to have a resting heart rate of 104 beats per minute, right? So this is the original claim. So our null hypothesis, mu is equal to 104 beats per minute. So here, a vet wishes to test to see if a new medication will lower. So there's that key word, lower, which this becomes a left tail test and a less than sign. And again, you see this value is the same in both the null and the alternate. Right, so mu is equal to 104, that's the original claim. And the alternate, will this new medication lower the heart rate? Well, if it does, then we accept the alternate claim here that mu is less than 104. And that's basically it, right? Not much to it. Okay, so going through, looking for the important number and then important keyword. Researchers think that if expectant mothers use vitamin pills, the birth weight of the babies will increase. Okay, so right there you see the word increase. Right, so we'd be dealing with a greater than sign. The average birth weight of the population is now currently 7.6 pounds. So the original claim is 7.6, and these vitamin pills we're testing to see if they actually increase the birth weights. So we're looking at mu is equal to 7.6 and then mu is greater than 7.6 for the alternate hypothesis. Moving on. A chemist invents an additive to increase the life of a car battery. If the mean lifetime of the car battery without the additive is 36 months, so that's the key word, does the additive have an increased effect on the life of the battery? So again, increased effect, you'd have a greater than case. So the null hypothesis, mu is equal to 36. The alternate, mu is greater than 36. And again, you can classify it as a right tail test, but we're simply just listing the null and alternate hypothesis for the time being. Okay, so last example here. A medical researcher is interested in finding out whether new medications will have any undesirable side effects. The researcher is particularly concerned with the pulse rate of patients who take medication. Okay, so currently, the pulse rate for the population is 82 beats per minute. So right away, you know that this 82 will show up in both the null and alternate hypothesis. Now the question at hand, for the alternate hypothesis, will the pulse rate increase, decrease, or remain unchanged after a patient takes this medication? So in this case, you don't know it's greater than, you don't know it's less than, so you test for both cases. This would be a two-tail test. And that's simply it for that example. Okay, so moving on to the next page. And this is a page you might want to highlight because really for the rest of this course, you'd be referencing this idea of a p-value. And making sure you can see this one since it's so important. Okay, so the idea of a p-value, you can read the definition from the book, but basically it's the probability of an event occurring by chance. Now, it might seem really easy on the surface, but if you want to get a really in-depth understanding, you might have to look into it a little bit in more detail. But the purpose of the p-value is that it's going to give you an understanding to the final results, and basically it'll allow you to formally accept or reject your original hypothesis. So going back to the previous page, you had two hypotheses, right? Mu is equal to k, and the alternate, mu is either less than, greater than, or not equal to k. So in the final conclusions, you would either have to accept the original claim or accept the alternate claim. And this is done so through the use of the p-value. Okay, so moving on. Just a few things to recall here. The test statistic is given in the problem usually as either x or x bar. And then to find the probability, you could use the z-table or more easily the norm CDF on your calculator. So again, not much is changing here, it's just that we're actually using what we've learned in the past lectures now in a more appreciative way in finding the p-value. Okay, so how to compare the p-values. Now in most cases in mathematics, a larger number means better things. But depending on how you look at it anyway, a large p-value here means that your test statistic of an x bar would fall very close to your population mean mu. So with that being the case, your p-value here would be the majority of the bell-shaped curve being shaded, so you have a large p-value. And here, x bar falls close to the original population mean mu. There's no real difference between what your sample gave you and what the population would be. So the results only vary slightly. So with this in mind, there's no real difference between the population mean and your studied sample. So with that, you would accept the original claim and say that there's no difference. On the contrary, if you have a small p-value, just make sure you can see everything all right. If you have a small p-value, you may have done a study where your x bar fell far from the population mean. This resulted in a very small p-value. When you have a small p-value, the x bar is going to fall very far from the original population mean. This might cause some might be a cause for concern because your sample mean is so distant from what is now known to be your original claim. So with this said, there is a distinct difference between the sample data and the population data with that big gap. Then results show that the sample data does not relate to the population data, so you might want to accept the alternate claim to say that there's a new norm. Right? So the results are statistically significant, and we would reject the null hypothesis and actually accept our alternate hypothesis, or what that would be considered your new norm. Right? So here, in this example, results are statistically significant, and in this example, results are not significant. So whenever you have a small p-value, you would reject the null hypothesis, and whenever your p-value is very large, you would accept your null hypothesis. So there's not enough information here to throw it out, but here there is. Okay, so going back to this is again a very, very important topic, right? Statistical significance. And this is how you would either accept or reject the null hypothesis, which is basically everything in the remaining parts of this course. So when you have your null and alternate hypothesis listed, right? So here mu is equal to k. Alternate, you would have mu is less than, greater than, or not equal to k. This is no longer your opinion, so the way we either accept the null or reject the null is based on our p-value. If your p-value is very small, meaning less than this level of alpha, then you would reject the null hypothesis and accept the alternate claim as your new norm. So, going through, the significance level is noted by the Greek letter alpha. Okay, and this is always given in the problem. Okay, so really to run through this, you list your null and alternate, which is what we started today's lesson with. Then once you have your null and alternate hypothesis, you would then find your p-value using your calculator. Once you have your p-value, you would compare it to your alpha level, which is given in the problem. Once you have this comparison, if your p-value is small, like we saw on the previous page, right, small p-value, your results are significant, meaning you would reject the null. So again, when you have a p-value that's very small, you reject the null, which is described right here, right? When your p-value is less than alpha, then you reject the null hypothesis because your data is very extreme. Right? So you would have your population mean, and your x bar would fall very far from your population mean. Right? So like you see here, such a big difference between the two values of x bar and mu. But we'll get to that in the next sections, but it's a really good idea to make sure you have a very concrete understanding of what that actually implies. And the picture on the previous page would actually show you time and time again why that's the case, right? Okay, so the last part of this section is dealing with the types of errors that might come with statistical testings. Now, every type of statistical test is subject to have some sort of error, although you can actually find these different types of errors. So now, for instance, even though your p-value might be very small, and this is leading you to rejecting the null hypothesis, in all reality, maybe it was a bad sample, or maybe it was a bad sample design. Maybe your X bar wasn't really linked that well to what it should have been, and it gives you a bad interpretation of the overall population data. Keep in mind, an X bar is simply just a sample mean. X bars can change if you use one sample compared to another sample. So if you have a bad sample, this X bar might be really extreme, whereas if you try to test a different sample from the same population, it might be really close. So these samples kind of fluctuate back and forth. Now, the types of error. The type 1 error states that you want to reject the null hypothesis when it was actually the truth, which in all reality says you got a small p-value when you really shouldn't have. So the notation here, to I guess summarize what the type 1 error would be your alpha measure. And something I like to do in a right-tail test, let's say you have your population mean and you have your X bar. All right, you can actually label this as like your regions for rejection and your region for accepting. This is getting a little bit more into it, but basically anything to the right of a specific X bar, in this case right-tail test, you would reject the null hypothesis. Anything to the left you'd be accepting. And again, the reason why to the right would be rejecting, to the left you'd be accepting, was because anything to the right in this case might be smaller than an alpha level that was given to you in the problem. This is going a little bit more in depth than we want to go, but if you wanted to kind of get a better grasp on it, you can really think about what these values actually indicate to you. Okay, so type 1 error, you want to reject, or the conclusion states to reject the null when it was actually the truth. Next, the type 2 error. You failed to reject the null hypothesis when it should be rejected. So basically here, you keep the original claim, but your sample mean tells you that you should keep the original claim when in all reality the sample isn't really that great of a sample, and you should actually reject the claim to say like there should be a new norm in town. Last, the power. This is something that if you actually perform a statistical test in some sort of capstone course, this is something that will come up time and time again. And this is basically the probability of rejecting the null hypothesis correctly. So ultimately you want this to be 100%, but in the real world that really doesn't happen all that often. So now I think we have one example to go through, and then our own example to kind of write out what these different errors show us. Okay, so given the following situation, list the null, alternate, and in your own words, explain what the type 1 and type 2 errors would be. So a researcher wishes to test whether people use debit cards on average more than 11 times per month. Okay, so more than signifies a right-tail test, which is why we have a greater than sign. The 11 times per month is seen in both the null and the alternate hypothesis. Now, for type 1 error, this is when you reject the null hypothesis when it was in fact the truth. So if we reject it, that means that we're going to state that people use their card more than 11 times per month, when in all reality, they only use it 11 times per month, right? So if we performed a study and the final conclusion was to say that people use their debit cards more than 11 times per month, right? That's what our conclusion said, right? We rejected the null and accepted the alternate, but in reality, people only use their debit cards 11 times per month, right? We should have kept that null. On the contrary, the type 2 error, it's when you fail to reject the null when you should have. So basically in that case, if you fail to reject the null hypothesis, your final conclusions would say people only use their debit cards 11 times per month, when in all reality it should have been something more than 11. And I think we can read that on the next page. Right, so type 2 error. Just making sure you can see everything still. Sorry, it goes a little bit crooked there. Type 2 would occur if our results suggested that people use their cards 11 times per month, when in all reality, they use their cards more than 11 times per month. Okay, so let's try 2 examples, and then I think we're done with this section. Okay, so first things first. List the null and list the alternate. And basically, you can start every problem like this, right? H sub 0, mu was equal to some number, H sub 1, mu, and then we have to pick between 3 different cases. So full-time PhD students receive an average salary of $12,837. The Dean of Graduate Studies at the large university feels that his PhD students earn more than. So $12,837 is the number that we're going to use for both. And he believes that his students earn more than this, so it should be a right-tail test. Now, for the type 1 error, in this example, you want to reject the null when it was actually the truth. So, final conclusions. Would say that PhD students earn more than 12,837, when in reality this is what they earn. Right, so we rejected the null hypothesis when the null was actually the truth. And the type 2 is just the reverse. So this is when we failed to reject the null when we should have. Right, so final conclusions. State that PhD students only earn $12,837, when in reality it is more than this. And that's basically how you would summarize these different types of errors in English. Okay, so for type 1 error, the way we would describe that, the final conclusions would say that PhD students earn more than $12,837. Right, so we reject the null hypothesis, when in reality, this is what they earned. Right, so we should have actually kept the null. Type 2 error, the final conclusions state that PhD students only earn $12,837. Right, so the story is reversed now. So here we failed to reject the null when the alternate was the truth, meaning in reality that they earned more than that, right? So we should have accepted that alternate. Okay, so last example here. What are we doing in the levelness here? Okay, so the average length of largemouth bass in College Lake is assumed to be 14 inches. And however, you feel as if it is smaller. So the null hypothesis, mu is equal to 14. The alternate, mu is less than 14. Okay, so for type 1 error, we reject the null when we should not have. Okay, so this, conclusions, point to the fish size being smaller than 14 inches when, I like the in reality aspect of this, when in reality the average fish is 14 inches long. Right, so here we rejected the null when we should have accepted the null. So we reject the fact that it's 14 inches, right? So we're going to claim to the fish size being 14 inches or less than 14, when in all reality 14 inches is the actual size of the fish in the lake. Alright, and then finally, type 2 error. And this is what you might be asked to do on a test, right? Simply just list out what the errors might indicate. So the type 2 error, you fail to reject the null when this was actually when the alternate was actually true. So fail to reject when it should have been rejected. So conclusions state that the average fish size was 14 inches when in reality the fish size was less than 14 inches. And that's it. That's how you would actually summarize these things in English. And again, the reason why these errors might occur is based off of a bad sample. So, whereas a sample might lead you to one conclusion, so again, a sample like an X bar, it might be really far from the mu, but this could have just been a bad sample, right? So the probability of type 1 error occurring or type 2 error occurring, it really depends on your sample size and your final conclusions. But then again, if you go fishing one time and you catch a really big fish, it might throw off your results. If you were to go fishing again and you had a different result and you caught fish more around the average, right? You're still fishing from the same lake, so you're just getting two different sample sizes or two different sample means. However, one might say to reject the null, the other might say to accept the null. And when that's the case, you're going to have two different conclusions based off of the same fish out of the same lake. So that's why these different sample means might lead you to different conclusions, which is why we have these different types of errors occurring. You can actually find these different values for the errors, although all that I'm concerned with is can you actually just describe what the errors are indicating to you. From here, you have a few different assignments, and for whatever reason, these assignments got chopped off, right? So the first assignment is listed on this page, but just be aware that you want to flip this page over because there is just a few more assignments on the back page, but that's all described in your course calendar. So if you have any questions, let me know, and hopefully this helped out.